All right, hello Dr. Snow and future CBE 310 students. Today we'll be walking through finding the transition state of a chemical reaction of interest using Avogadro, ORCA, and IBOView. Here I have a comprehensive guide on how to find the transition state. I'll be walking through it a little bit today. It'll also be linked in the description of this video in case you want to walk through at a bit of a slower pace. But since this concept is pretty visual and there's a lot of stuff to cover, we're also recording this video. The reaction we'll be working with today has to do with aspirin. So as we know, aspirin is a very common anti-inflammatory agent. It actually works by targeting an enzyme in your body called cyclooxygenase 2, or COX2. It ends up covalently modifying COX2 by acetylizing a side chain on the enzyme called serine 530. Serine 530 is near the active site of COX2 and it results in a conformational change that inhibits the binding of a native substrate and leading to irreversible inhibition of COX2. For a little bit of context, COX2 is an enzyme that is several steps up the ladder that eventually leads to the expression of inflammation. So by inhibiting COX2, you inhibit the expression of inflammation down the line. It's not super important that we know how COX2 works, but it is important that we know how aspirin and serine interact and how aspirin acetylizes serine. So this is the curved arrow mechanism for our reaction. Right here we have aspirin, also known as acetylsalicylic acid, and right here we have serine. In a normal reaction, serine would actually not be an individual molecule. It would be attached to the backbone of the enzyme at this hydroxyl group. But for the sake of this reaction, it's a bit unreasonable to try to model the entire enzyme. That would be way too many atoms for these programs to compute. So I've just left serine as an individual molecule. Note that aspirin starts as acetylsalicylic acid and ends as salicylic acid because it's given that acetyl group to serine, which becomes acetylized serine. It's not always necessary to know the curved arrow mechanism of your reaction, but in this case I do know it, so I will be using it to find the transition state. There are several different ways of eventually finding your way to a transition state using ORCA, Avogadro, and IBOView. Ultimately, what we want to do is run a command through ORCA that will optimize the transition state geometry and run a numerical frequency calculation. We'll cover a little bit more on this later, but essentially these two commands will confirm that you've correctly identified a transition state of your chemical reaction of interest. However, to run these commands, you need a guess for the transition state geometry of your reaction that is going to be near to the real geometry. So it needs to be a pretty accurate guess. And there are two main ways to find that guess of your transition state geometry. The first is the relaxed surface scan. This is a method that's very good for simple bond making or breaking reactions or possibly conformational changes. It's a method that will tell ORCA to scan over a vector or a bond of interest and try to find how the atoms might interact as they get closer or farther apart along that bond. This can only be used for elementary steps in a reaction. So for example, with my reaction with aspirin and serine, this is the very first step of my reaction. So what's going to happen is there's a negative charge. If we look back up here, a base has taken away this hydrogen from the carboxylic acid group, and it's going to relieve that carboxylic oxygen with a negative charge. It's going to attack that hydrogen on the hydroxyl, and then that charge will find its way over to the oxygen on our serine atom. So this is one step of my reaction that I will be modeling with the relaxed surface scan. If I were to model the entire reaction, I would need, I believe, 3 or 4 more relaxed surface scans to complete this reaction and then find the transition state between every individual step, which for me isn't completely ideal since this is a multi-step reaction. So I actually ended up primarily using the second method we'll be talking about, which is the nudged elastic band method. This is a black box method, so that basically means you give the computer the inputs and the outputs and you don't really see what happens in the middle. But I really like the nudged elastic band method because all you have to do is give ORCA the reactants and the products, both optimized, and then ORCA will find a pathway between those two conformations with the lowest energy path. So you can actually So both the relaxed surface scan and the nudged elastic band, I'll be calling it the NEB, will give you a minimum energy pathway, which means that as ORCA scans either along that bond or along that pathway between reactants and products, it will be constantly optimizing the geometry of your reactants to be at their lowest energy state. And along that path, you'll actually end up with one state that's got more energy than the rest, and that's your transition state. So hard to visualize what I'm talking about if you just look at a normal activation energy graph. Let's move my face. You can see here that you start with your reactants, and this is Gibbs free energy. You go up, you hit a transition state, and you come back down. So this is basically a minimum energy path. If you look at this very highest energy right here, you're going to find your transition state geometry. So that's what we'll be looking for with both the relaxed surface scan and the nudged elastic band method. I would mention that as of the time of recording, the NEB command can actually only be run on the latest version of ORCA, which is ORCA 4.1. This version of ORCA is not the same as the one that is currently installed on the computers on CSU's campus and the VPNs. So I was only able to run the NEB on my personal device. That is something to keep in mind if you're thinking about using this method. Here's a quick runtimes table of how long it took me to run all different calculations that I did. This is not the full table. The full table is linked right here. There's a lot of information, but I just wanted to give an idea for the potential transition state seeker of how long a calculation might take depending on the number of atoms you have and the command that you're giving ORCA. Some of my calculations took a lot longer than I was expecting. Some of them never converged, so it's just good to have an idea of how long things might take if this might be able to help you. Moving on to the first step for either your relaxed surface scan or your NEB, whichever you may choose, is to do geometry optimizations of your reactants. This should be pretty familiar as this is something we tackled in CBE 310, but you're going to want to open Avogadro, draw your molecule. I'm going to open a file that I've already drawn just for efficiency's sake. These are my reactants. So this is aspirin on the left and serine on the right. I actually optimized both of these molecules separately, and then I brought them into the same file and I optimized them again before using them in any of my calculations. That geometry optimization should be pretty straightforward. I'm going to go ahead and assume that you know how to do it. If you don't, there is a bit of a walkthrough right here. I will mention you do have to remember to put the correct charge and multiplicity in for your molecule. If you don't do that, ORCA will get confused and give you an error message. Once you have optimized your geometries for the relaxed surface scan, you're good to go and start making your input files. And we'll cover that in just a second. But if you're running a NEB, there is an additional step. So like I said, the NEB will take our geometry optimization XYZ file. So that is just the pure Cartesian coordinates of every atom in your molecules. It'll take a reactant file and a product file, and it'll find pathways between the reactants and the products. To do this, ORCA needs every single atom in your reactants to match up exactly to every single atom in your products. What I mean by this is that if ORCA is trying to get from A to B, and atom 1 in the first conformation is atom 16 in the second, it's not going to be able to make that pathway, or at least not the pathway that you want it to make. So to make sure that every single atom is the same, you're going to want to hit label. This will give a number to every atom. It's worth noting that Avogadro doesn't automatically give atoms, every atom a unique number. I think it labels it by symbol or like atom type and then molecule type. To change that, you're going to want to hit this little toolbar right here. Take atom number, whatever it is, change it to atom number. That will give every atom a unique number, which is how ORCA will read your input file. So basically, these are my reactants. This is just acetyl salicylic acid and serine. And what I want to do is make a products file so I can then optimize it and then put it into my NEB scan. So what I want to do is, without creating any atoms or deleting any atoms, I want to make my products out of these atoms. And this is where it's really handy to know your curved error mechanism. Because I, for instance, know that during the course of my reaction, this hydrogen, hydrogen 30, will attach to this oxygen 14, and then this carbon 15, is going to come take that hydrogen 30's place and attach to oxygen 22. And then that oxygen 30 will move down to oxygen 12, or hydrogen 30 will move down to oxygen 12. I know my curved arrow mechanism very well at this point just because I've been working with it for so long. So I can just do this by moving atoms. So I'm not going to delete anything and I'm not going to add anything, but I'm going to take, I think I actually want to take my carbon 15. I want to select all of these atoms right here because everything attached to this carbon 15 is going to move with it. I want to take all of these and move them towards carbon 22. This is a bit hard to see, but I'm going to move them towards, sorry, that's oxygen 22. And then I'm going to delete this bond. I made it bigger. I'm going to delete this bond. And then I'm going to take hydrogen 30 and move it down towards oxygen 12. And I'm going to delete this bond. This is where, when you've clicked on your little bond editing tool, unclicking adjust hydrogens is very helpful, because as soon as I deleted this bond, Avogadro might have been inclined to make an extra hydrogen to fill up that extra space, and we don't want that because we know that at the end of this reaction, there are going to be no extra hydrogens than there were in the first place. So the products has the same number of hydrogens as the reactants. So we don't want ORCA making anything extra for us. And then we're going to reattach the bond right here. And then we know we want carbon 15 right here and carbon 22 to attach. So we're going to reattach those two. Now this may look a little wonky. Rest assured, you can click extensions, optimize geometry, and there you go. You have two things that look remarkably like the products we're aiming for. And if you'll notice, no atom numbers changed during the course of this, this change from reactants to products. So now what you're going to do is file, save it as a new product file, run it through a geometry optimization with extensions, ORCA, generate ORCA input, change geometry optimization, change your charge. I'm going to assume you know how to do all that. What's really going to matter is that you end up with an XYZ file for both your products and your reactants. So this is my neb folder where I've kept all of my things related to my neb calculation. Right here, I have my reactants XYZ file, so that is completely optimized, a geometry optimized reactants file, and a completely optimized product file. And those are going to be two of my inputs to the neb. So if you're going to be doing a neb, make sure you get those steps right. And we're going to hop back to talking about the relaxed surface scan for just a second. So we're going to talk about the input for a relaxed surface scan, and this can be a little bit confusing. So just to review, for this relaxed surface scan, I want this singular step to happen. I want this oxygen to attack this hydrogen and this charge to end up on this oxygen on the serine. To do this, I tell ORCA that I want to scan along one vector or one, it's almost like an imaginary bond. I can also scan between 2 points in space. If you're curious about that, you're going to need dummy atoms. I recommend this video tutorial. But if you're just scanning between two atoms like I am, this bond in green is where I want to scan. Then you can just use those atom numbers. So I'm going to pull up Avogadro again and go back to my relaxed surface scan input. So you can see here that I know the two atoms I'm interested in are this hydrogen 21 and this oxygen 14. Now these are numbered differently from the neb because they're different files. It doesn't actually matter in this case, but I need to know that I'm interested in hydrogen 21 and oxygen 14. And what the input to a relaxed surface scan will look like is something like this. So this is my command line. It's telling ORCA that I'm using reduced Hartree Fock. I'm doing a single point calculation. I'm using a basis set of def2 SVP, and I want to optimize it. Then this command block right here, this is called a geometry command block. And what it's saying is that with regards to the geometry of this molecule, we want to scan along a specific bond. And that is going to be the bond between atoms 13 and 20. It's worth noting that the numbering schemes between Avogadro and ORCA are different. So if we go back to our input, remember this is carbon 14, or oxygen 14 and hydrogen 21. So Avogadro numbers atoms 0 or 1 and up, and ORCA numbers atoms 0 and up. So when we're making an ORCA input, we have to remember to reduce the number of our atoms by 1. So 13 and 21 will become or 14 and 21 become 13 and 20. So between bond 13, 20, they're starting 3.084 angstroms away from each other, and they're going to get 1 angstrom away from each other, and it's going to take 12 steps. Now, since I've messed with this input file, since I did my relaxed surface scan, these numbers are a little bit different, but you can use your distance tool right here. You click on the atoms that you're interested in, and Avogadro will tell you how far apart they are right now. So right now they're 1.354 angstroms apart. So I moved this entire serine atom a little bit closer since I did this reaction. But you just start, you check what your farthest distance apart is right now. You're going to input that into your initial distance apart. This is how far apart you want them to go, and this is how many steps ORCA is going to take. This is just your XYZ file. This is your starting coordinates. This -1 means that the charge on my molecule is -1. So that's the setup of that bond command. And so every time that you run a relaxed surface scan, you'll have to redo the bond that you want to optimize, and how far apart it is right now, how far apart you want it to be, and how many steps it's going to take to get there. And the output of your relaxed surface scan it's going to give you a number of files. Every time ORCA runs a calculation, it'll give you a whole handful of files, XYZ, GWB, interp files, output files. There's all sorts of fun stuff. The ones we're really interested in are going to be the XYZ file and the output file for our relaxed surface scan. So we know the surface scan is done when ORCA tells us that it's terminated normally. I'll actually open my output file for my relaxed surface scan so we can look at it together. I'm going to be looking at attempt 4. Wrong attempt. I'm going to be looking at attempt 2. I've run so many of these, I apologize. I'm going to look at this output file. If you scroll down just a little bit, you can actually see all of the input you put in. That's the wrong file as well. Goodness gracious me, it's this one. You can actually see the input file. So now I can double check that I scanned along bonds 3 and 4. So this is a different configuration from 3.084 angstroms to 1 angstrom in 12 steps. If we scroll all the way to the bottom, we see that ORCA terminated normally, and actually everything under relaxed surface scan results is what we're going to want. So if we go back to our walkthrough, this is the same set of numbers. You'll find two chunks of numbers. One is the calculated surface using the actual energy, and one is using the SCF energy. We want this section, the calculated surface using the actual energy. What you're going to want to do is take these numbers and copy them into an application that can graph them. I heavily recommend MATLAB because these will all copy as one giant chunk. These are the very same numbers as were in that output file. Just confirm. These are the very same numbers. I've just copied them into MATLAB. I've made them into a giant matrix, and then I've said everything in this first column is a step size, and everything in this second column is an energy. So what this is the step size in angstroms. So if you'll remember, we ran that bond from 3.084 angstroms to 1 angstrom. And then these are the corresponding energies for every one of those steps. So when I've taken those points out and I've plotted them. So when we run our plot, this is what we end up with. This is our minimum energy pathway. And so what we can look at here is as our bond started at 3.084 angstroms, as the bonds get closer, as that oxygen and that hydrogen get closer and closer, their energies are going to go up, hit a local maximum, come back down, and then they shoot off into outer space. The reason for that is that as the atoms get too close, it's not actually, it's not actually possible. The reaction will get atoms closer than they could experimentally get, so the energy shoots up. So what you're actually looking for is a local maximum. So this step right here is going to be our step of interest, because if you think about that activation energy graph again, this is going to be looking very likely to be our transition state. With relaxed surface scan graphs, you count your steps from right to left, because you start at 3 angstroms and you go to 1 angstrom. So this is step 1, 2, 3, 4, 5, 6. We can actually confirm that that is the correct, in Avogadro, that's what I'm looking for. We can actually look at the trajectory of this calculation optimizing itself. this one. So you're going to have the name of your file, mine's attempt 4 input, and then underscore trajectory. It's going to be an XYZ file. You can open these in Avogadro, and then we can actually see what this animation looks like in real time. So this has 310 steps. I'm going to say dynamic bonds so I can see the bonds stretching, and loop, and we can just watch as this relaxed surface scan brings those two closer and closer together. So this already happened. Now it's just see they get too close. That's when the energy starts to shoot up. But if we watch, we can actually see that hydrogen move bonds around step, 80 or so. So you can kind of watch a reaction in progress, which is really cool. Trajectory files are a lot of fun and a great way to make sure that your reaction is on track as you go. So that is what your output for the relaxed surface scan is going to look like. Basically, all you get from it is that you can qualitatively say, it looks like it's going to be step 1, 2, 3, 4, 5 that is going to house the transition state. Moving on to NEBs. NEBs are a little bit different in that they don't need any direct output ORCA generated input file or from Avogadro. So Avogadro generated ORCA input file. They don't need one. You can kind of just make your own input file. But before you get there, there are 3 types of NEBs, just to cover them quickly. The first NEB is the most vague, it's the most crude estimate of the transition state. The second NEB is a bit more computationally expensive, and it will give you a climbing image guess for the transition state geometry. So it will use kind of a vague minimum energy path convergence, so it's not going to be as specific for the entire path, but once it finds a geometry that it thinks is the transition state, it will have a high convergence threshold. So it's going to be a more accurate guess of the transition state to then put into your optimization of the transition state and your numerical frequency calculations later. Last but not least is the NEB TS keyword, so NEB transition state keyword. This one's my favorite and it's the one I used. It is also definitely the most computationally expensive. What the NEB TS is going to do is it's going to find your minimum energy pathway with a medium convergence threshold, so like fairly accurate. It's also going to find you a climbing image guess for the transition state. And once it finds that climbing image guess, so what ORCA thinks is going to be the closest to the transition state, it'll automatically feed it into a transition state optimization calculation, which would have been the next step for the relaxed energy scan or the NEB and NEB CI calculations already. So this one just does it for you, which I think is pretty cool. And then if that converges, it will give you both the climbing image guess in your initial pathway and the actual transition state geometry, which is great because then it's just already run and you can run a numerical frequency calculation after that. Worth noting, it does take a little bit while because it's doing so many things at once. So an input file for a NEB is going to look something like this. It's a lot simpler. This is just my input file. I used B3LYP basis set and the def2 SVP. I use the NEB TS keyword, and then I have this NEB command block. In this command block, I have specified that the NEB and XYZ file is going to be my optimized products XYZ file that came out of my ORCA geometry optimization for my products. And I say the XYZ file that we're starting at has a charge of -1 and is going to be the reactant optimization XYZ file. I can open these up. We're back to the NEB. I can open these up. All these are XYZ files. It's a bunch of coordinates. So it's telling ORCA start at these coordinates and finish at these coordinates. And it looks like a bunch of gobbledygook to us, but they're slightly different and ORCA will recognize that and find a pathway between them. It's worth noting that when I actually ran this calculation for the first time, I ran out of geometry optimization cycles, and so my output didn't fully finish. It finished, it just told me it didn't converge on a transition state geometry. We can actually look at that output file. So we see the input is just the same one I just showed you. We're going from the reactants to the products. If we look at, it did not take long for the NEB to converge. It takes a lot longer for the geometry optimization cycles. So we look at the NEB path summary. This CI right here stands for climbing image. This is the step that ORCA thinks will be closest to the actual transition state geometry. So take note here that this goes from 0 to 9. So there are 10 steps or 10 images here I'm going to count them 0, 1, 2, 3, and Avogadro is going to count them 1, 2, 3, 4. So we'll just keep that in mind as we move forward. So ORCA thinks that this will be step 3. We'll also come down to the bottom. As you can see, this took 4.5 days to run, and it did not actually optimize my geometry because I reached the maximum number of iterations. That's not a big deal. I just took the last known output from this NEB calculation, the last known geometry, and I just put it into a new geometry optimization, and that ended up converging. So it's not the end of the world if something doesn't fully converge. But if you want to up the number of geometry optimization cycles so that it might not, your calculation might not terminate early, you can do that by adding a section to your your command line. So this is a NEB block. You'd add a geom block just right after it. Max iter for max number of iterations, and you can put your max number here. For some of my calculations, they took several thousand iterations. The ones that really mattered all usually took less than 100 or 200. So you can always do more max iterations than you think you'll need because ORCA will stop once it hits the ideal geometry. It will not use all 4,000 iterations you give it if it hits it at step 24. But you do need enough time to let ORCA run if you do a large number of iterations. So once your NEB optimization has converged, you can start looking at finding that minimum energy pathway and that guess for the transition state. So ORCA is really sweet. It already gave us a guess for the transition state. If we felt so inclined, we could go ahead and open that file in Avogadro and take a look at what ORCA thinks that transition state is going to look like. So remember, it was image 0, 1, 2, 3 was the one it thought would be the ideal transition state. This is what it looks like. You can kind of see that we've got this floating molecule in the middle. It's come from right here and it's on its way to right here. And this hydrogen is already transferred from this oxygen to this oxygen, and it will end up in this oxygen. So another really fun thing to look at, I told you I like the trajectory files. We're going to look at the mean energy path trajectory file for this reaction. So we're going to look at the animation. These are the 10 steps that ORCA gave us. So if you remember in that output file, that is this one, way back up at the top. ORCA gave us these 10 steps. It's these same 10 steps just made into geometries. Don't know what happened there. Made into geometries and shown here in Avogadro. So dynamic bonds on, loop on. I'm going to put this at a lower frame rate because I know it moves really quickly. And we can actually watch the bonds being made and broken and moving around. So this is really great because this reaction actually almost exactly follows my predicted curved arrow mechanism. You start with the oxygen, upside down. You start with this hydrogen transferring to this oxygen. There it goes. And then this oxygen is going to attack this carbon. And that carbon is going to break its bond with this oxygen and move over to here. And then this hydrogen is going to move from this oxygen to this oxygen. There we go. So that's the full mechanism that I would expect to see. This is the minimum energy pathway as opposed to the initial path. It just means that these are the minimum energies at every step. That looks really good. Like qualitatively, visually, that looks like what I'm looking for. And you can kind of see here, we can qualitatively confirm that the transition state is probably at image 4 because this is that image right, there's a bond there and there's a bond there. And so this little transition molecule is just hanging out by itself right around step 4. So that looks like a pretty good guess of the transition state. Worth noting that it's not super critical whether Avogadro chooses to form a bond here or there. You can easily imagine those little dotted lines like half bonds that you draw between these two. It's really just some parameter somewhere that tells Avogadro whether to actually draw a bond or not, so don't put too much weight on it. So those are 2 ways we can qualitatively check the transition state of our NEB output. And then the third thing we can do is actually make a minimum energy pathway like we did for the relaxed surface scan. So what you're going to want to do for that is open your NEB files. It's going to give you a whole bunch of output files, but it's also going to give you one that is an interp file. So it'll be the name of your file.final, and it's just a bunch of energies, distances, and images. So you're going to want to take this and copy it into MATLAB once again. Close that. So these are those same numbers. So there's a small chunk and there's, whoops, a large chunk. These are the same, they represent the same steps. It's just the longer chunk has more points in between, and then ORCA condensed all of that into 10 steps just for viewing ease. And what'll happen is if we run this calculation, this MATLAB code, I've just taken the images, I've plotted the images, so reaction pathway against the energy. And this is the output that we get. So once again, this is the short output, so the 10 steps, and this is like 80 something steps. I've given it both circles just to see the individual points and a line just to get an idea of what's happening, how the points are connected. So as you can see, the bottom graph is really just the top graph with a little more detail. It hits a local minimum and a local maximum here that this less detailed graph might miss, but what we really care about is this very top step right here. This very top point is the same for both models. I can't really click it, but it's the same. There we go. And so this is going to be, once again, our guess for the transition state geometry. Our guess for the transition state geometry will occur at step 0, 1, 2, 3. So all three of our ways of checking our transition state guess for the NEB are matching up. Everything's looking really good. So we can move on to running a transition state optimization and numerical frequency calculation. So this is really the critical step where we confirm our transition state geometries, our transition state's geometry, and that it's actually a transition state. The way we do that is through these two commands, opt_ts and numFreq. The opt_ts is an ORCA command that will start with an approximate transition state geometry and then converge to the actual transition state and optimize the geometry at that transition state. There are several different ways to do this with either an approximate Hessian or an exact Hessian. A Hessian is just, it's a tool to help the optimization converge and like keep it on track. You can really only use, this is the approximate Hessian version of this opt_ts numFreq command. You can really only do this if your guess happens to be very, very close to the transition state, and you got to be a little bit lucky for that to happen. Most likely you're going to need to run a couple Hessians. This is computationally more expensive, but it keeps the reaction on track, so hopefully we'll take less iterations than just making a approximate Hessian. So if we scroll down to my actual code for this command, I used a PM3 opt_ts command, so find that transition state and optimize it, and then run a numerical frequency calculation on it. And then in this geometry block, I said calculate the Hessian in the beginning. It's a numerical Hessian. And then recalculate the Hessian every 5 steps. And then also you have 2,000 iterations to do this. Luckily, I didn't take all 2,000 iterations. I believe it only took 82 iterations and 5 hours to converge. So that's what your geom block is going to look like if you want to use numerical Hessians. Just returning to this numFreq command, I've explained it already, but what it's going to do is find every vibrational mode of your transition state geometry, and then if you've got one imaginary mode, one negative mode, you're on the right track. You found a transition state for your reaction of interest. The numFreq always needs to be run with an opt_ts command or an opt command. Reason for this is if you run a numerical frequency on a geometry that's less than optimized, you're going to get a lot of noise and some strange vibrational frequencies, probably multiple imaginary modes, which is not going to be super accurate. So you always want to run it with an opt_ts command just to be sure. The output for this is going to look like this. You've got your vibrational frequencies. Every time ORCA calculates a Hessian, it will recalculate your vibrational frequencies for you. I actually had like 101 modes or something, but here we are at mode 6. We've got our one imaginary mode, which means that that confirms that we have in fact found a transition state for our aspirin-serine reaction, which is stellar. That looks really good. If we want, we can actually open that up in, I'm going to close some of these. We can open that file up in Avogadro. What you're going to want to do is go to where you've run your optimization. And here you can see I have an input file, an output file, an XYZ, and a trajectory file. I want this XYZ file. This is where I ran my optimization of the transition state and numerical frequency calculation. And Avogadro crashed. And so in that file is going to be our said and done, optimized transition state geometry. So I'm just kind of curious what it looks like. So I'll go ahead and open it up. I'll turn those labels off. Okay, so we can kind of see that instead of floating like in that step 3 of the neb, we can kind of see that Avogadro decided to draw that bond between these two. The hydrogen has moved from the serine to the aspirin, so we're kind of in the middle here, and this is our transition state geometry. So now that we have that, you can also run this calculation on the relaxed surface scan. I ended up just doing it and making the walkthrough on my neb output because the neb was the main method that I used for finding my transition state. But now that we found that, we can go into visualizing molecular orbitals in IBOView. And for this, you're going to need the remote desktop. I'll just sign in really quickly. Because IBOView is a very graphics heavy program, so you're going to need something like the GPU to sign on to it. I think it just got confused. Where am I? There we go. I'm just going to renew my Pulse Secure connection. If you don't, oh no, I messed up. If you don't know how to access the GPU, I did make a tutorial. Oops. Hello. Currently connecting. That's not good. Here we go. I did make a tutorial. It's linked right here. It's just a PowerPoint on how to access IBOView via the virtual lab. So the normal computers on campus have an option where you could either choose, I think the computers in Scott Bioengineering at least have an option where you can choose whether to log into the GPU or a VPN. If you're going for IBOView, log into the GPU. Because that's the graphics processing version of the VPN. And then you can go ahead and open IBOView. So we are going to look at 2 different ways to look at our reaction of interest. The first is going to be our mean energy path from our neb scan. So remember that mean energy path where I was showing you the molecules moving back and forth? This is that same exact file, that trajectory scan. We can go into data sets here, frames. Orbitals will show up here once we calculate them, but frames, and we can actually move our reaction. And so we can see that, or IBOView actually knows that minimum energy path that we made on MATLAB. It sees it, and so it knows it's step 1, 2, 3, 4 is our transition state at that very tip there, and it'll keep going down. So you can move your reaction around. What you're going to want to do is go into Actions and Files and click Compute Analyze Wave Function. What this is going to do is allow you to make your actual orbitals so you can watch them move. I click both these numbers, these boxes at the top, charge of -1. Make sure you put in the correct basis set. I use def2 SVP. You click Calculate. This will take a couple minutes to run because this mean energy path has 10 steps. In the meanwhile, we'll open another window of IBOView and take a look at our actual transition state, So this is the file that we were just looking at in Avogadro. It is the transition state optimized geometry. We're going to go ahead and open it here. Looks familiar. We talked about this bond being connected. And we're also going to compute the wave function for this one. Once again, charge of -1, basis set of def2 SVP. Yes. This will take not very long at all to run because it's just 1 frame. It's worth noting IBOView does not use basis sets of the 6-31G basis set, so don't use those during your optimizations. And also, I would recommend against trying to calculate a wave function for a trajectory file or an XYZ file with more than 10 steps, just because if you're trying to make an animation, you do need to save every photo for every step individually, so it's going to take a long time to compile those. It's also going to take a long time for IBOView to calculate more than 10 steps. I had a couple of reactions where when I put them into the Avogadro trajectory to watch them animate, they had 300 to 2,000 steps, which just isn't going to go over well in IBOView. So we can see here that our wave function computation is finished for our singular transition state like geometry. So what we're gonna do is go back to data sets, and we can see that all of these orbitals have now been populated. There's 75 different orbitals. The first 10 or so are usually empty, but if you just start clicking, you can double click on one of these and you're gonna start loading some orbitals. And this is really fun. You can change the colors down here in render orbital, and you can change the shininess up here. It's all very fun. And then you kind of just got to click through and find the orbitals that you're interested in to actually look at. Let's check on our other reaction. Still calculating a little bit. To get an animation, you're going to, did it just finish? Beautiful. So this just finished our mean energy path calculation. So if we go into data sets, orbitals, we have all these wonderful orbitals. And this is how you're going to get your animation if that's something that you want. You can see once again, we can move current frame, watch our orbitals move. And now this track orbital button is usable. Whereas before with our single frame, you can't move this because it's one frame and it's one frame, you can't move it. But if we go back over to our mean energy path, our orbitals are now showing up. So how this works is it shows you your minimum energy path, and then you can scan through all your orbitals, 1 through 75. And then any orbital that's not a baseline energy, that's very exciting. So if the orbital doesn't change, it'll stay along this bottom line. If the orbital does change, its energy goes up. So orbital number 26 looks pretty exciting because its energy changes a lot, really close to our transition state. So we're going to click show 26. It'll show that orbital on our molecule. It'll also retain this energy path on our graph. So I'm going to keep scrolling through here and pick some, that one's exciting, pick some paths that I want to keep. That one looks fun. I have some predefined orbitals here that I'm aiming for because there are a lot of interest, but if you do too many at the same time, it can get a little bit confusing. So I'm just going to stick with these 4 for now. And then you hit Control T. This will trace the isoforms of all of your orbitals. So basically it loads them through every frame so you can watch them move, which we'll now do by either changing the frame down here or scrolling our bar right here. So we can watch our reaction go through its states. We can see at our transition state, we've got some orbitals that are stretching between molecules. This isn't our actual transition state, remember. This is the closest guess we got for our mean energy path, or minimum energy path from the neb output. So we can watch those orbitals move around, and you can also turn them on over here by clicking the orbital numbers. I'm going to go ahead and turn on some more. That one's a bit messy. They overlap a lot. And I'll retrace those isoforms. And then I'm going to go back and watch them all move. So if you want to make an animation out of these orbitals, you got to, I'm going to deselect these just because they do get confusing. You go to Actions and Files. You find a nice setup that you're happy with. I'm on step 0. I'll click Save Picture As, and I will save this picture into a file. You can see I've already done this with 2 different sets of orbitals. I've saved all my photos step by step. And then you go to data sets, you go up 1 frame, and you save the picture again. And then you go back and go up 1 frame, and you save the picture again. It is worth noting that once you have computed a wave function and gotten your orbitals, there's actually no way of saving that file for later use in IBOView. IBOView only saves things as a PNG or a Java file, and you can't re-upload that Java file into IBOView. So it's either once you've made your wave functions, save your photos, or just recalculate the wave function the next time you open IBOView. So you go ahead and save every frame for a reaction, and then you can compile them into an animation with some online editor, or even into a PowerPoint where you click through them really fast and the orbitals will look like they're moving. So my animation for those very same 4 orbitals I just left you with looks like this, if that looks familiar. And that is more or less where our walkthrough of finding the transition state with Avogadro, ORCA, and IBOView will end. Take note that there are more things you can do with transition states. For this specific walkthrough, we happened to model our reactants as if they were individual and as if they were not touching anything else. So as if they were basically gases. Whereas in an actual reaction, there would be solutes and other stuff. That might be a fun way to take this project in the future. You might also investigate reactions that have more than one transition state, so you can model more than one in IBOView. But for now, this is as far as we go. There's an extra section here on continuing calculations that have been terminated early that I'm not going to cover right now. But if your calculations do terminate ahead of schedule, don't freak out. There's ways to recover them. I also listed all of the work cited and then also those websites that I found useful while making this tutorial. So if something about my walkthrough just doesn't click with you, you can try any of these sites. That being said, I hope you had a wonderful time learning about transition states with me. Hope you learned a little bit something, and have a wonderful day.